Hello, I'm the Sultan of Astronomy, and in this video we will be looking at Wien's law, and we're going to use that to calculate temperature of stars, or we may go vice versa, use the temperature to calculate color. We will then look at some spectra, absorption spectra specifically, and based on that we can classify stars, and we can also learn some stuff about them, whether they're binary or not. Wien's law explains why stars are different colors, because we can assume that a star is like a perfect black body radiator, meaning that it radiates wavelengths of light based just on its temperature. So let's say that we have a cool star. It is going to be radiating temperatures something like this, with its peak wavelength right here. Now let's say we have a hotter star. Hotter star might be radiating different wavelengths, something like this, but its peak wavelength, where it really is the most awesome at radiating, is going to be a little bit shorter wavelength. This is the short wavelength area. And if you have a crazy hot star, it might be something like this. And so crazy hot has a shortest maximum wavelength. Medium would have a little bit longer, and a cool star would be red because its maximum wavelength is a little bit longer wavelength. Making a calculation with Wien's law is crazy easy. If you look in your IB Physics data booklet, you will have this equation, and this is the maximum wavelength, whatever wavelength the star is most awesome at radiating at, and this is the temperature. Clearly, it's going to be in Kelvin, because our units up here are meters and Kelvin. So take a minute, pause it, see if you can solve this problem. Now if you haven't, be disappointed in yourself, because all you gotta do is rearrange it to be your constant divided by your wavelength, which, remember, you gotta convert to meters, and remember, nanos times 10 to the negative 9th, those go away, and you end up with a temperature of about 6,200 Kelvin, which we do know that blue stars are hotter than our sun, which is a white star, and our sun has a temperature of about 5,800, and so it makes sense that a blue star should be hotter. You need to remember a little bit about absorption spectra. If you've forgotten it, go back to the atomic topic 7, look that up. You should remember, though, that if you look at the spectrum that's being radiated by a old school filament light bulb, you get every wavelength, Roy G. Biv. But if you look at that for a star, you have things missing. And there are colors missing because sometimes the outer gases of a star will absorb some of the light coming out of it, and that will take their electrons up to a higher energy level. And then if you see something like these lines missing, you can say, oh, that star has a lot of hydrogen that's not that hot and can absorb stuff. Or maybe that star has a lot of helium that can absorb stuff. And so these absorption spectra can tell you things about the chemical composition of a star. Now, what's also important is, let's say all these things, all these lines are all shifted to the left, farther than they should be. That's what we call, because it's towards the blue, we say it's a blue shift. And that means that the star is coming closer to us. And so we can know of a star's motion towards or away from us, because it'll be blue shifted if it's coming towards, and you can probably guess if it's going away from us, it all goes the other way. And this, I'll even change the color for you. How about that? Would be a red shift. And if it's red shifted, that means it's moving away from us. Within our galaxy, some stars are moving towards, some stars are moving away. With other galaxies, most of them are moving away, but we'll get to that later. You could also look at different parts of a star, which I think is really clever. And if one side of the star is, let's say, red shifted, as it should be, The other side of the star, you can probably guess, would be blue shifted, because the star is going to be spinning. And we can then tell things about the rotational speed of that star, which I think is pretty clever. All stars can fall into a certain spectral class based on their temperature. And it's sort of a strange system of classifications that is O, B, A, F, G, K, M. And you can remember that with a simple acronym, O, B, A, fine girl, kiss me. Or guy, kiss me, whatever you're into. And over here on this end, the blue stars, you can probably guess that these are all the hot stars. Over here, these are the cooler stars, like red giants. And our sun is going to fall into this category. And now it's not a clear definition that a star just goes from white to suddenly blue. It's, there's a blue-whitish stars as well. Many stars are binary, meaning that there's two of them, and they're orbiting around each other. The simplest type is a visual binary, meaning just what you see there, that if you could look through a telescope, they'd be close enough to you and with enough distance that you see two distinct points of light. And, for example, if this bigger calculator were being orbited by this smaller phone, then they would always be opposite each other. This big one would be going slower than the small one. Life would be more awesome if you could just look up and see all these binary stars rotating around, but usually they're too far off and they're too close for us to know. And if you were to look at a telescope, you'd say, oh, that looks just like one star. But if you have a clever light meter and you hook it up to your very awesome telescope and you measured the light intensity over a few days, these eclipsing binaries, they might be orbiting in the same plane that you're looking along. And so you've got a really bright star orbited by a smaller, maybe dimmer star. And when the dimmer star goes behind, the light intensity would drop like you see at A. And then it gets over here and you get full intensity again. And then it might drop when the smaller star blocks the bigger one, like at B, and you get your lowest intensity. Then back to full. And then back to C, and then it goes back to full, and then the smaller one blocks it back to D. Now maybe you've got two stars that are orbiting around each other, and you can't tell that they're separate. They're not a visual binary. They never eclipse each other. But let's say you look at the spectral absorption lines on it, and you might see at first that you've got some lines that are maybe here, here, and here. And then you look later, and now they have shifted over here towards the blue end. That's a blue shift. And then a few days later, they've actually shifted over to here. That would be a red shift. Well, then you know that something crazy is happening to that star. And that might be because you're analyzing the light of the brightest star, and that star happens to be coming towards you when you get the blue shift. And maybe at the bottom on what you're looking at, you get a red shift as that star is going away from you. Now again, that's the spectral lines that are shifting that will tell you that.